Hello, wonderful people. Today, we're going to explore an intriguing discovery made in one of the oceans, right here on Earth. It's about a massive crater that had been hidden for millions of years, caused by an impact so powerful that it generated an enormous tsunami. The effects of this event are still observable today. Personally, I've always been fascinated by impact craters, possibly because of my childhood interest in dinosaurs. After all, the extinction of the dinosaurs was caused by a massive impact event. Because of this, I've always been curious about other potential collisions and the effects they might have had on our planet. In this video, we'll dive into the latest discoveries related to this newly found underwater crater and discuss what we know about it so far. But let's start by addressing a common point. Given the size of our planet and what we see on the Moon, it's obvious that Earth has been hit by numerous objects throughout its history, and its surface should be covered in craters. In fact, it might have been covered in craters in the past. However, due to powerful erosion, plate tectonics, and ongoing geological activity, most of these ancient craters have been erased or significantly altered over time. Only a few craters are still visible today, and many of those are located on the continents where erosion and geological processes have been slower to erase them. Interestingly, Earth's oceans make it even harder to find these craters. Since oceans cover so much of the planet's surface, finding craters in the water is a much more difficult task. Over millions of years, most of these craters would have left behind only faint traces. However, in the last few decades, some of these hidden oceanic craters have been discovered. In fact, one of them, which we discussed in a previous video, could be associated with a major climatic shift. Off the coast of Africa, about 400 kilometers west of Guinea, there's a feature in the Atlantic Ocean that's about 9 kilometers across. This feature was likely formed around 66 million years ago, roughly the same time as the impact that wiped out the dinosaurs in Mexico, known as the Chicxulub crater. The newly discovered feature, named the Nadira crater, is believed to have been caused by a much smaller asteroid, possibly around 500 meters across, and is located 300 to 800 meters beneath the seabed. So, alongside the much larger Chicxulub impact crater, we now have evidence for at least 2 significant impacts around the same time, possibly from a single parent body. Additionally, there's evidence for what's referred to as the Allen impact. This impact, which we'll explore in more detail in a future video, is thought to have occurred in the Pacific Ocean. While no crater has been identified, there are signs of an ancient tsunami and iridium, anomalous substances typically linked to asteroid impacts. The timing of this impact is also significant because it coincides with a period of cooling on Earth, and some theories propose that it might have triggered the ice ages. This rock, estimated to be between 1 and 4 kilometers in diameter, struck the ocean where the depth was at least 4 kilometers. This impact likely evaporated the asteroid completely, preventing the formation of a traditional crater. Now, let's focus on a recent discovery that adds to our understanding of underwater impact craters. Thanks to new research, we now have confirmation of a rare underwater crater located beneath the North Sea, which has been dubbed the Silver Pit Crater. Although this crater has been suspected for decades, it wasn't until now that scientists have gathered enough evidence to prove that it is indeed the result of a massive impact and not some other geological phenomenon. The Silver Pit Crater lies about 130 kilometers, 80 miles off the coast of Yorkshire, United Kingdom. It was first discovered back in 2002, but during that time, scientists were primarily focused on oil and gas exploration in the North Sea. At the time, researchers found a circular feature that could have been the result of a variety of causes, but pinpointing its exact origin was difficult, especially since it was buried under about 700 meters of sediment. The feature itself spans 3 kilometers, 2 miles across, which made it large enough to be significant, yet too deep to immediately understand its formation. For over 20 years, there was considerable debate within the scientific community about the true cause of this structure. Some suggested it was a result of geological processes, like salt deposits or volcanism, a hypothesis that was favored by the Geological Society of London in 2009. But despite the debate, there was always the possibility that this was an impact crater, though it lacked concrete evidence until now. In 2025, A new study finally settled the debate with the help of high-resolution, three-dimensional seismic imaging and detailed analysis of rock samples. The results were clear. This structure was indeed an impact crater. The evidence came from the discovery of shock minerals, which are minerals that undergo pressure-induced rearrangement under extreme conditions. Shock lamellae, microscopic pressure deformations in minerals such as quartz and feldspar, are a key indicator that an object impacted at hypervelocity, causing the extreme pressures needed to create these unique structures. To create such shock effects, pressures between 10 to 13 gigapascals are required, which are typical of asteroid impacts. The seismic data also helped further confirm the impact origin of the Silver Pit crater. Complex crater features, such as a central uplift beneath the crater floor, and concentric folds were detected, all of which are characteristics of a large impact event. Secondary craters, smaller depressions that form around the main crater due to debris thrown out during the impact, were also visible in the data. These secondary features are rarely preserved on Earth due to erosion, but they were clearly present in the Silver Pit crater, further supporting its impact origin. Now that we have enough evidence to confirm its origin, we can begin to estimate the timing and size of the impact. The Silver Pit crater is thought to have formed during the Middle Eocene epoch, roughly 43 to 46 million years ago. The impactor is believed to have been at least 160 meters in diameter, much smaller than some of the larger known impactors, but still large enough to cause significant damage. When it struck the shallow sea, it would have likely generated a massive tsunami, possibly reaching heights of 100 meters. Simulations of the event suggest that the impactor struck at a low angle from the west-northwest, producing an explosive event and sending debris in the same direction. With the confirmation of the Silver Pit crater's impact origin, an important question arises. Did this impact have any significant effects on Earth, similar to the impact that caused the extinction of the dinosaurs or the one that potentially triggered the ice ages? Understanding the potential global consequences of such an event requires looking at what was happening on Earth at the time. The impact occurred during the Middle Eocene, a period marked by a relatively warm climate known as the Eocene optimum. During this time, the planet's temperature was significantly higher than it is today, and the Earth's polar regions were ice-free. However, there were no major shifts in the Earth's climate at the time, which raises the question, did the Silver Pit impact cause any major disruptions to the planet's climate or biosphere? The short answer, based on the evidence we have so far, seems to be no, at least not on a global scale. While the Silver Pit impact certainly caused significant local destruction, including the formation of a massive tsunami in the North Sea, there is little evidence to suggest that it caused any lasting changes to Earth's climate. Unlike the Chicxulub impact, which is widely believed to have triggered a mass extinction event, or the Allen impact, which may have contributed to the onset of the ice ages, the Silver Pit impact does not appear to have caused any major climatic shifts. The Eocene optimum climate continued relatively unaffected, and there is no strong evidence linking this particular impact to any global cooling or long-term atmospheric changes. However, the Silver Pit impact was still an event of immense local significance. Based on the computer simulations of the event, the impact would have caused an explosion of immense magnitude, sending debris and water surging outward in all directions. The tsunami generated by the impact would have been catastrophic for the surrounding areas, particularly the coastline near the impact site. While it might not have had a global effect, it would have certainly had a profound local impact, causing massive flooding and devastation in the North Sea region. The remnants of this event are still preserved in the geological record, offering us a unique glimpse into the destructive power of asteroid impacts. One of the key reasons why this impact didn't cause global climate effects may be due to the relatively small size of the impactor, at just 160 meters in diameter. It was much smaller than the asteroid responsible for the Chicxulub impact, which was around 10 kilometers across. Larger impacts are more likely to eject vast amounts of debris into the atmosphere, causing a global nuclear winter effect by blocking out sunlight and cooling the planet. However, the Silver Pit impact was relatively small, and while it caused significant local damage, it didn't have the same potential to disrupt the global climate. Despite this, the discovery of the Silver Pit crater is still incredibly significant. For scientists studying impact events and their potential effects on Earth, adds to the relatively short list of confirmed underwater impact craters, which includes the Nadira crater off the coast of Africa, the Chicxulub crater in Mexico, and the signs of the Eltonian impact off the coast of South America. The fact that the Silver Pit crater is so well preserved under the seabed offers a unique opportunity to study how impact craters form and evolve over time, especially in underwater environments. The discovery also contributes to our understanding of the hazards posed by smaller objects in the solar system. While large asteroids and comets are well known for their potential to cause massive destruction, smaller impactors, ranging from 100 to 500 meters in diameter, represent a significant, but often overlooked threat. These objects are plentiful in the solar system, and while they might not cause global extinctions, they can still have devastating local effects. The Silver Pit impact serves as a reminder that even relatively small objects can have significant consequences when they strike Earth, particularly in densely populated areas or near sensitive ecosystems. In addition to understanding the effects of past impacts, the study of craters like Silver Pit helps us prepare for potential future threats. With roughly 20 to 30 other proposed underwater craters still awaiting confirmation, scientists are using the techniques developed from studying the Silver Pit crater to look for other hidden impact sites beneath the oceans. These craters could hold crucial information about Earth history and offer valuable lessons about how to protect our planet from similar impacts in the future.